Hello everyone! Today we are going to be doing some acid-base water chemistry. So I've got a nice problem here set up that we're going to work together and solve, so let's take a look at it. A solution of pure water is dosed with 0.001 molar phosphoric acid. Using the graphical solution to determine the pH and complete solution composition. Okay, so in order to solve this, the first thing we're going to want to do is just list out all our species. H plus, OH minus, we're in water. Phosphoric acid is H3PO4, and then we're going to have to list all the protonated species, so H2PO4 minus, HPO42 minus, and PO43 minus. And once we know all of those, we can set up our equations, and most importantly, we need our pKa's. So over here, let's set up our deprotonation equations. So starting with phosphoric acid to dihydrogen phosphate, that's got a pKa of 2.15. And then next one is 7.2 and 12.3. These pKa values exist for all acids. You can look them up in a textbook or just online. They're available anywhere. You're going to need pKa's to solve any acid-base problem. So definitely going to want the pKa first. That's one of the first steps. So we know our equations now. We've got our pKa's. We've got all our species. So next step is to just set up our graph. So like it says in the problem, we're going to be using the graphical solution. So the first step here is to just get our x and y going. X-axis is pH from 0 to 14. Y-axis is going to be the log of the concentration from 0 to negative 14. So that's the log of the concentration of whatever species we're graphing. And then we're going to have two 45-degree x's, one for H plus and one for OH minus. And then to start off solving the problem, that's our initial setup. We're just going to draw a straight horizontal line at log of negative 3. That's going to be our concentration of our acid. So we know that we have 0.001 molar phosphoric acid. So 0.001 is the same thing as log minus 3. 1, 2, 3. So we're going to draw a horizontal line here. And then the next step is to look at our pKa's. And for each pKa value that we have, in this case, phosphoric acid is a polyprotic acid, so it has 3 pKa's, 3 H plus ions. So for each pKa value, we're going to match up the pKa along the pH axis and draw vertical lines at each pKa. So here is the 2.15, 7.2, and the 12.3. Once we have that all set up, we're going to find our system points. Our system points are going to be where the concentration and the pKa's intersect. So right here, and right here. These are our three system points. And then we're going to want to draw 45-degree angle lines going off of those to the next pKa line. So it's going to look like this. These sort of beige lines are going to come down 45 degrees until they touch another pKa line. So each of these sections that's divided off by the pKa's is going to represent a different section here. And then lastly, after one line crosses a pKa line, the slope is going to double. So right here we got 45 degrees, and now the slope is going to double. So it goes from slope of 1 to 2. So slope of 1 to 2. And then these lines drop off here, you see, as it crosses these pKa lines. So we're starting to get a little bit messy here. We've got a lot of lines on our graph, but all we have to do now is smooth these out. So we're going to smooth out these lines here, these 45-degree lines, so that they cross over with our horizontal concentration line. And we're going to smooth these out, and then we can just erase all the vertical pKa lines, and we can erase this concentration line, and then we're just left with this. So this is our final graphical solution for the phosphoric acid at this concentration. We have all of our species here. This is what it looks like. And so now that we have this, we can start to solve this problem. So we have the graphical solution all set up. So what we have to do now is set up our proton balance equation. We're going to set up an equation with the positive charges on one side, negative on the other. And then we can start making assumptions. We're going to need to make some simplifying assumptions in order to pinpoint exactly which intersection marks off the correct pH in this scenario. So we can make a few assumptions here. Phosphoric acid is a fairly strong acid with a pKa of 2. It's a very low pKa. So I'm going to make the assumption that it's a strong acid, and this is an acidic solution. With those assumptions, I know with an acidic solution that OH minus is going to be negligible. OH minus is only going to be abundance in basic solution. Because it's strong acid, it should fully dissociate or almost fully dissociate. So the phosphoric acid itself is going to be negligible for this. And then because, again, this is an acidic solution, we're going to cross off these two over here, the phosphate and the monohydrogen phosphate. So those should be negligible too. And then we're just left with the hydrogen ion and the H2PO4. And that point should fall right about here. That is where these two intersect, the H plus and the dihydrogen phosphate right here. And so once we find that point, that's our answer. And we just draw a line up, and we see that's at pH 3. Looks about 3.0 from the graphical solution. So we know now that the solution is at a pH of 3. And so from there, we can find the concentration of all the other species just by drawing a vertical line down, looking at all the points where the lines intersect, and then coming across and finding their log concentration. And then once we have their log concentration, we can just go 10 to that power, and we have all the concentrations of the species in our solution, the entire solution composition. That's it. That's how you do it. That's the graphical solution for solving acids and bases. Thanks.